Oh, so when we started section A2, I mentioned how, that it could be the top and the bottom, or the left and the right, and we always did top and bottom. So here's what would happen if we had left or right. So here's some examples. So find the area of the region bounded by y equals square root of x, y equals x minus 2, and the x-axis. Okay, so in this case, there's the first one we've seen that has 3. So here's y equals x, here's y equals x minus 2, and here's the x-axis. So there's the region that's bounded by all 3 of those. Okay. Excuse me. So we have that region. Now, if we were to look at, remember before we were making our rectangles like this, that's no good in this case to have the rectangles going up and down, because you can see here it uses this function as the top and this one as the bottom, but over here you would have a different function at the top and the bottom. Okay? And that's no good. You want to make sure that as you draw that rectangle, you always have the same function as the top and the same function as the bottom if possible. So let's put the little note. So you want the same upper bounds the entire time, and the same lower bounds the entire time. Okay, so that's what we want to make sure. So you want the upper bound to stay the same, and you want the lower bound to stay the same. I'm not saying that these are the same. No. I mean, you're always going to use the same function as the upper bound, and you're always going to use the same function as the lower bound. Okay, and if we went this way with our rectangles, that wouldn't happen. So we're going to make our rectangles this way. If we went side to side like this, we'd have that. This one's always going to be the top, and this one's always going to be the bottom. Okay, no matter where we put that. So, when I say top, it's more of that it's the right. So this is the upper, and this is the lower. Okay, because between my rectangle, you can see that in this case, the delta x is here. The change in x is that way. The change in y is this way. Okay, so the rectangle has a thickness of delta y and a width of dx, and that width is just the upper minus the lower. So which one's the upper? Okay, let me write my integral. So you can see my integral is in terms of y. Okay, so I need my upper minus lower to also be in terms of y. So I'm going to change it since it's going side to side. Okay, I'm going to take each function. Okay, and let's put a little note here. Since the rectangle, so since upper and lower are left and right, then set each equation equal to x. Okay. Now, before we had them all y equals. So because we're going left to right, then you're going to make it x equals. So we're going to take this guy, make it x equals, and I'll move this over, so it'll be y plus 2. And this one, I'll square both sides, and it will get x equals y squared. Okay. So we have to make some adjustments there because we need this tells us right here that we need to be in terms of y. So I'm just going to make each of these equations in terms of y, because this little thickness here that we have is in terms of y. These have to be in terms of y. So the upper minus the lower will be y plus 2 is the upper. Right, that's the upper one in terms of y, and then the lower one in terms of y is y squared. So we're going to have y plus 2 minus y squared. Okay. Now, as for our bounds, we're not going to put this in terms of x because this is in terms of y. So we need to think about how much is changing in terms of y. In terms of y, it's going from the lowest value of 0 to the highest value of 2. It's going between 0 and 2. Okay. We could have figured that out by setting the two equations equal to each other. Right? If you don't see it on a graph, you set the two equal to each other. Make it equal 0, factor. Okay, let me make sure I did that right. Something seems... now. Well, we don't need it. This one gives us another answer because we have this. It would have been over here too, and that's why we get that second answer. So we can see -1 to 2, but because it told us to stop at 0, that's why we have 0 as the lower bound. So it does go up to 2, right? We're just not going to go to -1. Okay. What do? You integrate this. If I integrate that, that'll give me y squared over 2 plus 2y minus y cubed over 3. That's the same. It's just the variable's different. You plug in your 0 and your 2. 2 plus 4 minus 8/3 minus, oh, that has 0. Great. Okay, so if 6 minus 8/3, 6 is the same as 18/3, so it's 10/3 there. Or if you want to, you can put it in mixed number form. It doesn't matter for that one. Okay, take a look at this next one here. Okay, my rectangles are going to have to go side to side. Okay, you can see the thickness is y, which tells us where our integral needs to be in terms of y, because that thickness is y. Okay, and then how the height of each rectangle is the change in x. How much does the x change? Well, okay, my equation here. Okay, how much does the x change? It looks like this one's the upper bound, right? Oh, that's this one right here. So upper minus lower. That's my change in the x. And so it's going to be 2 minus 2y squared. Okay? And if you're having trouble figuring out which one's the upper, which one's the lower, like which graph is which, right, then just kind of think of a point. And I thought the easiest point here was if x equals 0. If x equals 0, I can see y is 0 for this. And if x is 0, then y is... I'm sorry, I said x equals 0. I meant to say y equals 0. If y equals 0, then x is 0, and then x is 2 for that one. Okay? We can see from the graph where the intersections are -1 and 1. If you can't see where they are, then you set these two equal. 2y squared equals 2. Y squared equals 1. So y is plus or minus of 1. Okay? Remember, these bounds are in terms of y because this was in terms of y. So it's really just the same. We just have to change the variable we're working with. Antiderivative, 2y. Okay, bounds being 1 to -1. So we'll plug that in. 2 minus 2/3. Distributes in. So I get 4 minus 4/3. And that would be 8/3 for myself. Okay. So I'm going to do some more examples. If you feel like you got the hang of it, you want to try the homework files, go right ahead. You don't have to watch every single one. Okay. So let me go through this one here. Right. Not a bad idea to pause the video, give this one a try, and then look at it afterwards. Okay. My rectangles going left to right again, so that I can have the same functions as top and bottom. So there's my delta x. So my integral needs to be set up in terms of y, because that's the thickness. Right, so I need my upper and lower bounds in terms of y, and so I could get that by solving this one for x, and then setting these two equal. I know it's on the picture, but I'm just showing you how to do it if it wasn't on the picture. Set them both equal, set them equal to each other. Okay, so we get 0 and 5 as our y values. Okay, what's our larger and what's our smaller? Okay, this one's the larger, the line is the larger one, right? The larger x value. So that would be y minus 5. So we find the change in x, we do y minus 5 for this one, minus bottom one. Great, those cancel. Okay. Okay, so there we get this is our change in x. Okay, antiderivative now that we have it set up. Plug in. Okay, plug in 0, that's going to go away. So I'd have that. And that's not necessarily a fun one to try to figure out. It's a great one to use your calculator for. You just put 125 divided by 2 minus 125 over 3, and then use the fraction button to convert it to a fraction. That gives you 125 over 6. That's my area. Okay, so on this example 4, let's take a look at it. All right, you can see it's very similar, right, to the previous problem, just the second one changed a little bit. Okay. Now, how do I know that the rectangle is going to be left and right? Well, because I have the y squared there. That's the tip off. If you see a y squared, that means you're going to be having those left to right rectangles. Since I don't have the graph here, first thing I'm going to do is let me find my intersections. So let me solve this one for x first. So if I solve for x, I'll move that over. So it's going to be x equals 5 minus y, and I'll set the two equal to each other. Okay, move some things around. Okay, you can add y, and subtract, and we're going to factor. Okay, so that gives us two y values, 5 and negative 2. Okay, so my bounds are going to be negative 2 and 5 for this one. Okay, now how do I know which one's larger and which one's smaller? Okay, it does help that I kind of looked at the graph from before. Okay, right? And if you're having trouble with this, you can always put these into go to Desmos.com and you can graph any of these, right? But if I was going to think about this, like this graph, y equals 5 minus x. Right, that's going to look like that, something like that. Okay, this other one, let's say I didn't know what the graph looked like, right? Let me plug in a convenient value. I know it looks like a parabola, I just know it, and it's going to be moving left or right. Right? How about I just plug in 0 for the y and see what the x is? If I plug in 0, I get x is negative 5, so it's over here. Oh, remember the intersections are at negative 2 and 5? Right? So that means it's going to be something like this. So that I actually get those y values of negative 5 and negative 2. So it's going to have to open that way. If it opened this way, I wouldn't get those intersections. Okay, so that tells me if I make my rectangle, I can see which one's the larger one. This is the larger one. Right? The 5 minus y is the larger, and then the other. So 5 minus y squared plus 4y plus 5. And so I can combine some like terms. I get 10. Okay. So we now take the antiderivative. Plug in our bounds. So we get 50 plus 75 over 2 minus 125 over 3. Lower bound, negative 20. Right? Plus, let's see, that's going to be 6. And then plus 8/3. Okay. Distribute that negative in. So I'll get, let's see, 70, so it's 64 plus 75 halves. I'll leave that for now. This is going to be minus 133 over 3. Hey, look at that. That actually reduces. Does it reduce down? Oh, it'd be really nice if it did. Bummer. Right? Thought it did. Thought it did. Right? But it didn't. Okay. So it's another great one. Hey, let's use that calculator. 64 plus 75 divided by 2 minus 133 divided by 3. Okay. Change it to a fraction, and I got 343 over 6. I was hoping that wouldn't cancel, but it didn't. So sometimes that happens. Sometimes you get lucky and it cancels. Sometimes it doesn't happen. Okay. So we get that answer. That's how we do those problems.